So now that we've done a simulation of a whole plate, let's talk about symmetry. Because, when you look at the results from our whole plate, it was just round. And really, it didn't matter which direction we looked. The result was a circle. The grid maybe wasn't completely circular. However, the results seem to be really consistent. So let's look at symmetry. Here's our SolidWorks model that we started with this plate. Now I'm just going to look at the top view of this. So let's take this model, and we can take a slice through this part. I'm going to go back to the original sketch, and if I draw a line from the center up here, and if I draw another line from the center down here, then I can trim the parts. And I've got a half a plate. Now, that's still pretty symmetrical, but it's more symmetrical than just on that axis. Why not trim it more so? Let's go back and try that again. Why don't I trim it from the center, and I'll make that line horizontal. And it's still symmetrical. And in fact, it doesn't really matter where I draw a slice of this. It's always going to be basically the same. I could keep bisecting the angle and bisecting the angle, and I'll always get a result that is still symmetrical. So I can really just cut that as small of a sliver as I want. Perhaps what I want to do is make the inside arc about the scale of the grid points that I want to use. So I'm going to save that that slice of my plate under a new name. I'll just call it Gremlin Disk Slice. And I'll save it as a step file. And now back in ANSYS, if I want to create a new transient thermal analysis, and there's our slice. Now, we can start out the same as before, where we will choose materials, material assignment, and I will select body and apply, and I'll pick the material to be aluminum. And now with my mesh, I can look at the method of the mesh. I'll be picking the body. And here's where I could pick really any method I like, but I'm just going to once again let it go automatic. And then I'll choose sizing on the body and apply. And my element size, in the first example, I'd used an element size of 0.01 meters, so I'm going to do the same. And that seems denser than what I'd seen in the previous version. So I'm going to try to make that a bit bigger. Maybe that's too coarse. But it's not too dissimilar from what we saw in my preceding model. In fact, if I look at my previous model here, you can see that around the circle, I basically had 1, 2, 3, 4, 5, 6, 7, 7 elements around that circle. And right now I'm looking at, in this new model, I've got something about 1/8 of the circle, and I've actually got better resolution here. Because whereas this size would have been approximately 1 element, I've got 2 elements here in this diameter. So that might actually be better resolution than what I've seen before. Now in my transient thermal analysis, I'm going to add internal generation. I'm going to select the body and apply. And I'm going to choose 100. And for my convection terms, I'm going to choose faces. I'll pick the top face and the bottom face and that inside arc and that outside arc. And my ambient temperature, I'll give it the film coefficient of 10 like I did before. The ambient temperature I'm going to say is 0. Better apply that. There we go, 4 faces. So I've got the convection boundary layer. Now the only thing left is, what about these slices? Well, because there's symmetry, so if you can imagine on one side of the slice, it would have to be exactly the same temperature as the other side of the slice. That is, this surface and then the replicated part that it mates to next to it, the same temperature difference will, or the same temperature, if you've got the same temperature across an interface, then the heat flux across that is 0, because heat flux is driven by the temperature difference. So we could define that as a perfectly insulated surface, as was, whoops, that one. There, 2 faces. So both of them are perfectly insulated. Now I've got my initial temperature to set up. I want to set that up at 0 like I did before. I want my analysis settings. I want to have 300 steps. Actually, sorry, I want to have 300 steps. And we'll leave that. Now, the previous model, where I looked at the entire solution, took quite a bit of time to solve. So there we have the solution. You can see that we're still predicting the 0.01. In fact, the number is exactly the same within reason. And if we looked at the animation, the behavior of the animation is the same as well. And we can look at the graph at any particular time and see what the temperature is at any time. And so even though we've cut the disk up into a small segment, the result that we predicted in terms of the transient temperature is identical to what it was with the full disk. So what was the point of this? Well, we can use symmetry whenever you can find it in your CAD model to reduce the number of mesh points. By reducing the number of mesh points, you reduce the time it takes to solve the simulation on the one hand, but you may think, well, it doesn't matter to me, I'll just start the solution running and walk away and leave it. That's fair. If you do proper looking for symmetry and you can reduce the slice of the model that you're simulating, you can get better resolution of the result. You can do the simulation on a less expensive machine. You can do more simulations. All kinds of good things out of taking advantage of the potential for symmetry. So when you see a problem that you're looking at, always look for the symmetry and always try and figure out what you can do to reduce the number of grid points and yet still retain, as we did in this example, the same level of resolution on a physical scale sense of the solution. Now the question you ask is, what are the boundary conditions we use when we cut a model from symmetry? Well, the one that I've used in this example was to simply say, I know that if this solution is genuinely symmetrical, that on one side of the cut, the temperature due to symmetry will have to be exactly the same on the opposite side of the cut. Therefore, the heat transfer is going to be the same. So that means that's effectively a perfectly insulated surface. Now, if you're doing this in structural mechanics with forces, then you're going to look at a mirror image of one part will be adjacent to the next part. So just like there's no heat flux across the interface, there will be no motion across the interface of the cut if it's a mechanical solution. That means that's a roller support. So it means that on the cut face, nothing can move into the cut. However, the part can be allowed to slide all it wants parallel to the cut. So that's the boundary condition, which is the equivalent for the mechanical boundary condition. In the case of fluid flow, when we get to that, the same thing. Perpendicular to the cut face, there's no flow. There's no volume flow or mass flow across the face because of the symmetry. You can, however, have all the flow parallel to the face that you want, but there'll be none across. Likewise, there'll be no shear stress parallel to the face because the relative motion on one side versus the other will be zero.